we're discussing infinite sets, quite interesting topic in the field of mathematics, where you get to see how powerful logic is, and one has to strengthen the intuition, and there are many places where intuition will be really weak and logic takes the lead. And in an attempt to understand this theory, we started off with the simple infinite set, something that we have seen before, the set of natural numbers, integers, and so on. And subsequently, we started asking, can we compare two infinite sets? Intuitively, we think the set of integers is bigger than the set of natural numbers, and but whereas we were able to establish a bijection between n and I, due to which we concluded the cardinality of n and I are one and the same. Then we asked, can we look at cross product on n? And towards that end, we looked at n cross n. Subsequently, we proved that there is a bijection from n cross n to n. Therefore, n is countably infinite, I is countably infinite, as well as n cross n. And so there are many interesting sets that we come across in mathematics, in particular computer science. They are all countably infinite. All that we need to do to say that it is countably infinite is to establish a bijection between the set under consideration and n. Now what we will do, we will look at sets which are not countable. So now the question is this: are there uncountable sets? Are there sets which cannot be listed, which cannot be enumerated? So no listing or enumeration, so which means you can't list the set completely. You can't list everything in the set, and there is no ordering among any elements. So you can't talk about first element, second element, and so on. So no ordering among elements. Whereas if you look at n or I or n cross n, we were able to say here is the first element, here is the second element, and so on. We were able to come up with an ordering. Such an ordering is not possible for uncountable sets. Now the interesting part is, are there uncountable sets? Answer is yes. So we now prove that the set of real numbers is uncountable. In fact, to prove this, what we will do is, we will even consider an easier climb. We will show that the closed interval 0, 1 is uncountable. Okay? So we are going to prove this. Suppose this is uncountable, then this is a subset of R. A subset is uncountable, therefore it's superset. That's how the argument will be. So what we will do, we will run proof by contradiction. Okay, suppose 0, 1 is countable. Suppose 0, 1 is countable, meaning countably infinite. Okay. If it is countably infinite, then what all can be there? There exists a bijection from 0, 1 to the set of natural numbers, or you can say that there is listing, there exists a listing or enumeration. Correct? Now, listing or enumeration tells you here is the first element. Okay? So here is the first element, here is the second element, here is the third element, like that. So because it is countably infinite as per our assumption, Let me list the elements like this. Let the first element be 0 point, say 0, 0, 0, 0 something. Then 0 point something like 0, 0, maybe 1 somewhere. Then like this we proceed. So we may get something like 0, 7, 8, 9, 6 like this. Then 0 0.4, 5, 3 like this. Then 0.89 like this and so on. So we will be able to list elements like this. Now what I am going to do is the following. In general, how do we write this? This is just an example. So in general, you have 0 x11, x12, x13 like this. Then 0 x21, x22, x23 like this. Then x31, x32, x33 like this, and it goes. So this may represent, this is the first digit, second digit, third digit and so on. This may be something like 0, 1, 2, this may be 7, 9, 8, this may be 8, 9, 7 and something like that. Now like this, a listing is possible, correct? Now what we are going to do is the following. I am going to construct an element. Consider y which is 0 point, say y1, y2, y3, y4 dot dot. So how do we construct this? It's like this. So yi is 2 if xii is not 2. You look at this. If x11 is say 4, then y1 is 2. It's xii. I'm just focusing on the diagonal element. Then look at x22. Suppose it is 3, then y2 is 2. Then look at x33. Suppose it is 9, then it is 2. Then look at x44. Suppose it is 5. Okay. And then it is 2. Suppose look at x66. If it turns out to be 2, then what you do? yi is say 3 if xii is 2. So I am saying if the value present at xii, look at the diagonal elements, and now I am constructing an element y using these diagonal elements. Fine. So the way the construction goes like this. Look at the diagonal element. If the value is 2, then yi takes 3. If the value is other than 2, then yi takes 2. Fine. That's it. Now you see that y belongs to 0, 1. Correct? Because it is 0 point, y1, y2 and so on. It's clearly an element in this. And most importantly, y is not listed in this enumeration. Correct? Because it is not same as this. It is differing at this place. It is not same as this. It is differing at this place. Because what do we say? If xii is not 2, then this digit takes 2. If it is 2, then this digit takes 3. So which means it is differing with all of this at least at one place, or at least at the ith digit. And y belongs to this, and y is not listed in the enumeration. Correct? The reason y is differing with each of this, and now you see that y is differing with each element with each element in enumeration at least at the diagonal element or the ith digit. Correct? As per this, it is ith digit. Correct? So now, on one side we claim here is an enumeration, but on the other side we are getting a counterexample, or we are getting a contradiction. We are getting a contradiction that says that here is an element which is not listed in the enumeration, and we constructed an element y which is part of 0, 1 and not listed in the enumeration. Therefore, this enumeration is incomplete. And so our assumption that there exists an enumeration or there exists a listing of 0, 1 is incorrect, and such a listing is not possible. Therefore, the set 0, 1 is uncountable. Y is differing with each of this, so this implies that no listing exists. So our assumption that 0, 1 is countable is incorrect. Therefore, 0, 1 is uncountable. Now a subset is uncountable. This implies that its superset R is uncountable. Fine. It's a beautiful argument discovered by the scientist Cantor. It's called Cantor's diagonalization argument. So the idea is this: you assume there exists, it is countably infinite, then by definition there exists a listing or enumeration. So you focus on that. Then using that itself you construct an element and show that it is part of 0, 1 but not listed in the enumeration, and thereby you arrive at a contradiction, which means the assumption that there exists a listing is false. Thus you conclude 0, 1 is uncountable. Since it is a subset, therefore its superset is also uncountable. Now we identified an interesting set which we come across in mathematics and computer science at many places. You see that it is uncountable.